Hello and welcome back. This will just be a couple of examples working with probability, and I'll try to emphasize the multiplication rule and independence and dependence. So this is just kind of a fun example, and I can make a statement that it is more likely, more likely than not, in a room with 23 people, that at least 2 people will share a birthday. Now this seems a bit weird because there's 365 days in a year, not counting leap years for the moment, and we only need 23 people before it's more likely than not, as in the probability is greater than 50% that at least 2 people share a birthday. So let's go through this calculation. Let's call our people A, B, C, D, all the way up through, I believe it'll be W is the 23rd letter, just so that we can keep them straight. So person A has a birthday. Okay, that's a given. And then we want to calculate, so we're going to calculate the probability that, let's say that B does not share a birthday with A. Well, A will have a birthday on some day of the year, but B needs to not share that birthday. Well, there are 365 days a year, and if B doesn't share a birthday with A, and it's equally likely that B is born on any day, then there's 364 possible days that B could be born on. So this probability is pretty close to 1. 364 divided by 365 is very, very close to 1. So now let's think about this. So given that B doesn't share a birthday with A, what's the probability that C doesn't share a birthday with either A or B? Well, again, there's still 365 days a year, but now C can't share a birthday with A or B, so there are 2 days gone, but there's still 363 days left that C could be born on. D, again, provided that we know that all 3 of the first 3 people don't share a birthday, what's the probability that D doesn't share a birthday with any of them? Well, all 3 of these people have a birthday, so now there's only 362 days left. And we keep going until the last one, and I believe it'll be 343 out of 365, going through the same process. So the probability that W doesn't share a birthday with, singing your alphabet song, given that none of the previous letters share a birthday with one another. Well, there's 22 days gone, so this is the probability that W doesn't share a birthday with any of them. So then ultimately, the probability that no one shares a birthday would be the probability that B doesn't share with A times the probability that C doesn't share with A or B, given the previous one. And you can begin to see where this is going. The probability that no one shares a birthday is an AND. The probability that B doesn't share with A and C doesn't share with B or A and D doesn't share with A, B, or C. So because this is AND, we are multiplying. So it'll be 362 over 365, and we've got a lot of numbers in here. Oops. All the way down to 343 over 365. And if you add up or multiply all these numbers out, this is approximately 0.4973. So the probability that no one shares a birthday is about 49%, a little bit less than 50%, which means the probability that at least 2 people share a birthday, well, if at least 2 people share a birthday, that means that this isn't going to happen. These 2 events right here are complements of one another. If at least 2 people share a birthday, then this can't happen. If no one shares a birthday, then this can't happen. So not only disjoint, but they're complements of one another. So this probability is going to be the rest of the probability that this leaves behind. 1 minus 0.4973, which is going to be 0.527. So the probability that at least 2 people share a birthday is over 50%. So you only need 23 people in a room before it's more likely than not that at least 2 people will share a birthday. Which is, I think, just a fun little exercise. But one thing that's important is these probabilities change depending on if B shares a birthday with A or if B doesn't share a birthday with A. So all of this is because of dependence. If B shared a birthday with A, there's more days in the year that C could be born on. If B doesn't share a birthday with A, now there's fewer days that C could be born on to still avoid those birthdays. So all of this depends on the previous people not sharing birthdays. One of the uses of independence is in redundancy. So there's an example in the textbook on planes, and I've sort of modified this for elevators. So let's suppose that there's a particular elevator part. Maybe it's like a hydraulic piece of equipment or some cables, and it's rated at it has a 0.002 there's a probability of 0.002 of failing. So this means, so again, this is what, equivalent to 2 out of 1,000. And if we think about 2 out of 1,000, so this is saying that so 2 out of every 1,000 elevator trips, this particular part that we're talking about could fail. And that doesn't seem very small. An elevator could easily go up and down a day in say a busy city 1,000 times. So it would fail twice in that day. That doesn't seem very safe. So let's imagine that the elevator has 3 independent parts, and the elevator works as long as at least one of them is still functioning. So what's the probability of complete failure? Well, because they're independent, we can calculate these probabilities pretty easily. So the probability that, let's say that part 1 fails, is going to be 0.002. The probability that part 2 fails, given that part 1 failed, is still 0.002. Why? Because we're told that they are independent. They don't affect one another. And then the probability that part 3 fails, given part 1 and 2 failed, is again still 0.002. They're all independent, so the fact that one fails, it won't affect whether or not the other one fails because they're independent. So the probability of complete failure, the only way that complete failure goes is if part 1 fails, the first part fails, and part 2, and part 3, which is going to be 0.002 times 0.002 times 0.002, which happens to be 0.000008. I hope I did my math right. I think an easier way of looking at this will be This is 2 thousandths. This is 2 thousandths, and this is 2 thousandths, which is the same thing as 8 over 1,000, which is 8 billionths. So 8 out of every 1 billion times will the elevator fail. And that's a lot smaller than 2 out of 1,000. This number here, so 0.000000008 is a lot smaller than 0.002. So just by having 3 parts, this redundancy will save lots and lots of lives. So this is one of the important places that independence comes into play. Redundancy will save lives.